Okay, so we're starting 12.2 here. The majority of this chapter is on series, right? So we were just, the last section was really just a recap of some sequence stuff. We really are focused on series in this chapter. And so this is just kind of an introduction to series, and then as we move along, well, we'll see what we get. Maybe I'll do a couple different ones that are a little more natural. Okay, so this is what we mean by a series. So when we say series, for the most part I mean infinite series. And so it's really just asking you to add up infinitely many numbers, right? And so on the surface that seems problematic, right? What's 1 plus 2 plus 3 plus 4 plus 5? Obviously, if you go off to infinity, that's nonsense, right? It's going to get infinitely bigger, and so we don't have a great meaning for that. But this actually has a pretty natural meaning. So if you think of, you can do it in a bunch of different ways. I like to just think of a circle, but it doesn't matter. Think of a circle here, and let's say that the area of that circle is 1, right? All we're doing here is saying take half, add a quarter to it, right? Add an eighth to it, add a 16th to it, add a 1/32 to it, right? Obviously I can't squeeze any more in there, but as you keep adding half of what's left over, what do you think this sum should end up being? It should be 1, right? You're going to gobble up that whole circle and nothing more. Does that make sense? So this should be 1. We'll see this to be true in a little bit. But that's what we're kind of studying. Okay? Another place where you might have, where there's a pretty natural way to see this is to think of, let's see. Okay. So let's think of that. 3/10 plus 3/100 plus 3/1000. So what's 3/10? 0.3, right?
Yeah.
Plus, what's 3/100?
0.03.
0.03 plus
0.0030.
Right, and so each time you're adding more stuff to it, but you're always adding something smaller than the decimal places you already had, right? And so this looks like it should add up to be what? 0.333, so 1/3. Does that make sense? So this is the sort of thing we're going to look at in this, well, really in this whole chapter. The first thing we're going to do is learn about a couple sequences that always converge and always diverge, or series I should say. And then, well, after that we'll start getting tests to just decide whether a given series converges or diverges. For most of the chapter, we don't care that if we can come up with the exact value of 1/3 or 1. We just care if we can decide whether it does add up to a nice value or if it's poorly behaved. Okay? So let me give you some definitions here. Okay. All right. And so while I'm writing this out, let me just say, notice, right, every series, this is an infinite series, you add up A1, A2, A3, there's an underlying sequence, right? Number A1, A2, A3. So you have a sequence associated with it, and so there'll be a lot of interplay between the behavior of the sequence and the behavior of the series. And so you got to be careful about which one we're talking about at a given time. You've seen some of this before. What's the notation for adding a bunch of things together? Sigma. Does that look familiar? And so I'll just use I. I goes from 1, I sub I. And so back in Calc 1, when you were doing Riemann sums, you summed from 1 to n. Now we're summing from 1 to no end, right, to infinity. So it'll be 1 to infinity. And just like with sequences, these can start someplace other than 1. So you might have a sum from 0 off to infinity, or from 10 to infinity. Everything I write down to, will apply to all of that as well. Okay. So we want to decide what it means for this sort of thing to converge. And let me just come back up here. Okay. So we're going to define these S sub n's in a second. These will be called the partial sums. And they're just sum the first element, sum the first 2 elements. So 0.3 plus 0.03. Sum the first 3 elements. I'll just jump ahead. Does that make sense? So that's what we're going to, so that's what our S notation always means here. And so the nth partial sum oh, and I should also write this up here. There'll be times where we're sort of lazy about the sum from where to where. If we know sort of the underlying sequence, we might just write sum of the a sub k's, and you just sum up whatever that sequence is. So the nth partial sum of these guys is S of n, and again, it's just a1 plus a2 plus an. So you're just adding the first n terms of your sequence, or yeah, of your series or sequence. Does that make sense? Okay. And so now what that does is, given a series like this gives rise to a new sequence, right? Your S1 is just A1, your S2 is A1 plus A2, S3, A1, A2, A3. That gives rise, those are always going to be defined, right? They're a finite sum. So that gives rise to a new sequence, and we already know what it means for a sequence to converge, and so that's the definition of a series conversion. So I'll write it this way. If, now this is a sequence of those partial sums, if this sequence converges to S, then we say, what did we say? I'll write it like this. Okay, so if you have a sequence, or if your sequence of partial sums converges, then we say this series converges. Okay? And if it doesn't, then it diverges. So if this diverges, then we say okay. So the main point here is that all of the behavior of a sequence, of a series, comes down to the behavior of the series of partial sums. Okay. And so let's look at something that doesn't converge. So here's our question. Oops, can't spell. Does 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 converge? And so let me just say, this is a reasonable question to ask, right? We saw 1/2 plus 1/4 plus 1/8 plus 1/16 sort of naturally converge to 1. And so here the same sort of things happen, right? You get a number, you add a smaller number, you add an even smaller number, smaller number, smaller number, and so it's natural to think that maybe this converges as well, and so we're going to show that the answer is in fact no. But let's show that work. So let's look at partial sums, and I'm not going to do all of them. I'm going to pick specific ones that are useful. S sub 1 is 1. What's S sub 2? 1 plus, and I'm going to write it like this way, 1 plus 1/2. You can combine it if you want. And then I'm going to jump to S sub 4. So S sub 4 is 1 plus 1/2 plus, and I'm going to do a grouping here of pieces. Okay. So the 1 plus 1/2, I'm just going to leave that on all of these. 1/3 plus 1/4. Which one of those is bigger?
1/3.
1/3. And so this thing, right, is greater than if I replace that 1/3 with another 1/4. Does that make sense? But now what's inside the parentheses now? 1/4 plus 1/4 is 1/2, right? So S sub 4 is greater than 1 plus, and again, you could clean this up, but I want it to be written this way, 1 plus 2/2. Does that make sense? Try that same trick with S sub 8. Okay, so this will be the last one I write every term out. I'm going to do the same grouping I just did on these guys, plus then I'll group all the new stuff. Okay? And so in both of those groupings, just pick the smallest term and replace everything else with that smallest term and see what you end up with. The smallest term in that grouping. So like we just did here, replace 1/3 with 1/4, replace all those with 1/8, and what do you end up with? You get another 1/2, right? So if you do that, it'll be 1 plus 1/2 plus 1/4 plus 1/4 plus 1/8 1/8. And so the point is, those are all 1/2s, right? 2 1/4 and 4 1/8 are all 1/2. So you end up with now 3 1/2s there. Does that make sense? Okay. And so maybe I won't show all the details, but you can play the same game now as long as you just look at those powers of 2. And so S sub 2 to the n is always going to be greater than 1 plus n times 1/2. Does that make sense? I didn't show all the details, and don't worry about it right now, but hopefully you buy that that's true. So if that's true, what is 1 plus 1/2 times n? What does that go to as n goes off to infinity? So 1 plus n times 1/2, the limit as n goes to infinity of that. Infinity, right? Again, we're kind of abusing notation here. So that limit doesn't exist. And so that S sub 2 to the n is bigger than that. And so the limit as n goes to infinity of S sub 2 to the n has to also be infinity, therefore. The sequence of S sub n has to diverge. And so again, we kind of have this notion of it converging to or going off to infinity. That's also considered a diverge. So. And thus, the sum of this. Okay. And so the point is, right, that some infinite sums of things converge and some don't. And so that's what we're trying to figure out, is which ones don't. And I'll just say, sort of very vaguely, right, this one converged. I changed it around a little bit. Right, this will converge to 2. I added a 1 to what we had earlier, right, the 1/2 plus 1/4. This will converge to 2, and this will diverge. And like I said, on the surface, it kind of looks like you're doing the same thing, right? You take 1, you add a smaller number to it, an even smaller number. The point is, if you graph these things, this goes to 0 really fast. And this sort of takes its time going to 0. Right here. It's an exponential on the bottom, and it's just a linear thing on the bottom of this one. And so that's That's the big difference. So the original thing we showed converges because the terms go to 0 really fast. And then this, this guy here, this is known as the harmonic series. So maybe, I'll wait until we get a little bit further on. That's the harmonic series, and so the harmonic series diverges. That's an important fact that we need to have here. Okay. Yeah, let's do this before we do the geometric series. All right, I'm going to give you a little hint before we do the problem on this one. So, okay, if I just combine these guys into a common denominator, 1 over n minus 1 over n plus 1, what do I get? N plus 1 minus n, right? When I get that common denominator, so it'll be n plus 1 minus n, just 1. You get 1 there. So if you were just given this, you can figure out it's this using what method? Method of partial fractions. Remember doing that? We'll do some more of this as we go on. But for this first one, I just wanted to sort of give you the hint. Okay. So show that the sum from n equals 1 to infinity of 1 over n times n plus 1 converges, and find its value. So this is a type of series that we call a telescoping series, and you'll see why we call it that in a second. So let's just go off to the side. So we're going to do this. This is one of the places where we'll do just complete brute force on this thing. There's basically only 2 situations that we're going to encounter on a regular basis where you're asked to find the value or find the sum. Let me say sum here instead of value. Okay, so there's only 2 types of things where we'll actually look for the sum. One of them is this sort of telescoping series, and the other are going to be these geometric series. But let's work with this first. Okay, so my hint or my note over there said you could break this guy up like this, right? And let me just put parentheses in here to make sure we're clear, right? All of that is inside that sum, right? And so now let's just start writing down our partial sums. So S sub 1 is what we get when we plug in 1. So what's that? 1 minus 1/2. And I'll put it 1 minus 1/2. I'll just leave it like this for now. What's S sub 2? 1 minus 1/2 plus
Plus 1/3.
well 1/2 minus 1/3, right?
Okay.
Right, you plug 2 in then. So you plug 1 in, you get that, and then you plug 2 in, you get this.
Okay. All right.
And so now those middle terms cancel, right? And so you're left with 1 minus 1/3. Do it with the next 2. It might be overkill. But see what all cancels out and what you're left with after you sort of cancel out the appropriate things. The third term in this one. 1/3. 1/4, is that okay? And then, and so there's your sort of telescoping, right? You collapse it, you're stretching it back up. So there's where that terminology comes from. And the same thing here, 1/2 minus 1/3 minus 1/4. 1/4 minus 1/5, and again, the same things happen, right? And you get that. So, what do you think S sub n turns out to be? If we do this on it, you could write it out what it looks like to collapse, or just look at these examples, right? S1, 1 minus 1/2. S2, 1 minus 1/3. S3, 1 minus 1/4. 1 minus 1/5. 1 minus what?
Infinity?
1 over n plus 1.
Yeah, just think about that fraction that's left over, right? It's 1, and then that's 1 greater than where you were at. 1/4, 1/5. So 1 over and plus 1. Does that make sense? And now, what does that go to? So what's the limit as n goes to infinity of that Sn? And again, just think it, right? It's 1 and then minus 1 over something getting big. So that goes to 0. The whole thing just goes to 1. Does that make sense? And so therefore, your sum from 1 to infinity of this that make sense? And so anytime you have a telescoping sequence like this, if you can get a nice form for what those S sub n's look like, then you just take the limit of that. If it doesn't exist, then the thing diverges. If the limit exists, that's your sum. Okay? So hopefully that's not too bad. All right. So last thing for today, let's talk quickly about geometric series. So this is another place where we can get our sort of hands dirty and actually get nice values of a geometric series. All right, I'm going to do it with a real simple example, and then I'll jump back to the more sort of abstract, or at least a somewhat simpler example. Okay, a geometric series, this is just one of this form. And so the full definition is a little bit more complicated. It's really just throw an A in front of this, but for convenience, I'm going to ignore the A for a minute. Okay, and so just to be clear, this is, what do you get when you plug in 1 for n? You get r to the 0. What's that always going to be? 1. So it'll be 1 plus n is 2. You get r to the 1. Just that. Right? So that's what you get when you start adding up powers of a fixed r. Okay? And so the formula we're going to come up with requires us to start here at 1 or to start at whatever. So you'll have to tweak it when it doesn't work out that way, but we'll get to that in a minute. So, let's see. Let's just do this. So S sub k, that's going to be 1 plus r squared up to what? So you could do r sub k. I'm going to say r sub k minus 1. Right? That's really the first k terms is usually what the sum means, and we started at a 0 basically. Either way, it's not a big deal. If you're off by 1, you'll get the same value. But let me call it that. And then notice, what do I get if I multiply that whole thing by r? R times 1. R times r, and actually maybe I'll just write it like this, r plus r squared plus r minus 1, and then that times another r will be r to the k, right? So I'll get this. Does that make sense? Okay. All right. So let's do this. Do it in either order, I guess. I'll do it this way. Okay, let me do it. So if I take that S sub k and I subtract from it r times S sub k, on one hand I can pull out the S sub k, right? And I get 1 minus r times that. But if I just think of taking this f sub k and subtracting this guy from it, what do I end up with? So I just take this column, or that line minus this line. I get 1 plus r plus this minus this, right? So I get 1 r minus r squared minus r squared, right? And I work down, all of them cancel out except for that last guy. So I get that. Does that make sense? So this sum is also, this difference is also equal to 1 minus r to the k. And so we found now a nice closed form for these partial sums. They are 1 minus r to the k over 1 minus r. Does that make sense? Okay. And now let's just think about, so here. Anytime I put a little squiggle, you don't need to throw this in your notes. This is in your head. This is us. That's us thinking about that. All right, so let's just think about this for a second. 1/2 to the k, what does that go to? As k goes to infinity. Okay, I'll just write it up with limits. What's the limit as k goes to infinity of 1/2 to the k? It's 0, right? It's 1/2 times 1/2 times 1/2, right? So that's going to get smaller and smaller. That'll be 0. What about the limit as k goes to infinity of -3 to the k?
Is that -1?
No. Negative infinity is not bad. It's not quite, though. It's really, but the negative to the k is going to flip back and forth. So you're going to get big positive numbers and then big negative numbers. It's going to bounce back and forth.
1 over?
No, it actually just does not exist in no real way. It gets, you have some of them go off to infinity, some of them go to negative infinity, but there's no specific value you approach. What about 1,034 over 1,035 to the k?
0?
It's 0 again. Anytime you take, or even if I make it negative, right? It's anytime you take a number smaller than 1 and you start raising it to bigger and bigger powers, you go to 0. In this case, much slower than you did up here, but you still go to 0. Does that make sense? And so coming back to this, and so the limit as k goes to infinity of your s of k is 1 over 1 minus r if your r is smaller than 1, right? That's what we were just showing here. Anytime you take something smaller than 1 in absolute value, its limit goes to 0. So that just goes to 0. We get 1 over 1 minus r. And the limit as k goes to infinity of the s of k's does not exist. Does not exist. Oops. If the absolute value of r is greater than or equal to 1. Okay? So I'm just going to write this down now. Series. Okay, so the only difference between what we did and what we call a geometric series is we throw an a in front of it. This is a plus ar plus ar squared. So you're just taking some number and then multiplying bigger powers of r on it. Converges to a over 1 minus r if the absolute value of r is less than 1. And diverges if r is greater than or equal to 1. Okay. And so let's just look at this for the one example we've seen already. So that one we saw right at the start of class, or of this section, was a geometric series. What's your A in this case? This is a little goofy, actually. So this is a geo series with. So the R is pretty easy, right? What power do you keep bumping up? Powers of 1/2, right? So your R is 1/2. What's your A? Your A is also 1/2, right? It's always going to be your first thing that shows up. So you got to be careful when you set these up. We'll do more of these next time. But let me just start it off there. And so that's the value of R. 1/2 is less than 1. Well, the absolute value of R is 1/2 less than 1, and so the series converges to A over 1 minus R. So that's 1/2 over 1 minus 1/2, and that's. Right. Make sense? Okay. And so I think maybe I'll stop there for today. So let's cut it there, and then next time we'll finish. We have just a little bit more to do for this section, and then we'll move into 12.3.